Welcome to this monthly video. Today with us we have Pragalbh. He is a DMAT's third year over here in ISI Bangalore. His interest is algebra and topology, and he's going to give a talk about Zeeman's collapsibility conjecture. Over to Pragalbh.
Thank you everyone for coming. So today we are going to talk about Zeeman's conjecture, and of course I'll tell you what the conjecture is and what are some of its consequences. But you should also see this work as an introduction to piecewise linear topology. So we'll spend some of our time trying to understand basic results and Also I will not be providing proofs of a lot of things because we don't have that much time. And in some cases I only provide sketches of proofs. But I hope this will give you some idea of what all of this is about. Okay. So we'll begin with an introduction to piecewise linear topology, polyhedra. Well, the conjecture is about collapsibility of polyhedra, so you need to understand what that means. So a subset of Rn is a Euclidean cell if it is a constant of the finite linear points. And so for example, this is called the standard N simplex, and these are the basis vectors in Rn plus 1. Okay. Now P in Rn is called the Euclidean polyhedron. If it is a union of finite many of these Euclidean cells. Okay. So some observations you can make, and if you don't see it immediately, keep this as an exercise. If you have two polyhedra, so I will not always say P is always reserved for polyhedra P, Q, and eventually, so P is for Euclidean polyhedra, eventually we use K, L, etc. for Euclidean polyhedra, VW, etc. for simulation complexes, and yeah, so basically I will not always write down what these things are, but it should be clear. So these are polyhedra, then their product inside Rn plus 1 is also a polyhedra. If you have a linear map from Rn to Rn, then the image of a polyhedron is also a Euclidean polyhedron. And lastly, so by a hyperbolic section, I mean, so by definition this is inside some Rn. So I look at a hyperplane in Rn and intersect it with P, that is also polyhedron, Euclidean polyhedron. Okay. So now a map from P1 to P2 is called piecewise linear, which I abbreviate as PL, if so if this is inside some Rn, this is an Rn, so the graph of F inside Rn plus N is a Euclidean polyhedron. So now again some things you should know. Identity map from P to P is PL. And composition of piecewise linear versus piecewise linear. I mean, you could see this in several ways. One way is the graph is x comma x where x is in P. So you can directly see what these points should be. It's the same thing that works for P. Or another way to see this would be to look at the product P cross P, and you know that hyperplane sections of Euclidean polyhedra are polyhedra. So you just one by one put the constraint that first one and the n plus one, these are the same. So you one by one you put these constraints, that is like intersecting with the hyperplane, and in the end what you get is a Euclidean polyhedra. And same for this one, you can use this to prove this. Okay. Now, so suppose X is unique topological space now. So you want to define what is a PL structure on X. Piecewise linear structure. And a PL structure on X is a maximal collection of polyhedral charts. So what do I mean by that? That means I have a family of maps which are in fact embeddings and these are all Euclidean polyhedra such that they are uniting the whole space. So they cover your entire space, and for all I and j there is a k such that so we assume it is maximal in the sense that if I add any more map here, it does not remain compatible. So by compatible I mean this holds such that Fi inverse Fk and Fj inverse Fk are piecewise linear. Okay, so if you know about manifolds, this definition is similar to that, except it is not yet. So these spaces may not be manifolds. For example, if you have something like this, even this is allowed. So you see the reason why this is not a manifold is points like this. So we will soon make a definition of a piecewise linear manifold. And yeah. Okay. Now a map. So now these are PL structures. So if it is PL with respect to the polyhedral charts, then the map is PL. Okay. Now here's the thing. If you have a Euclidean polyhedron, then the identity map from P to P gives you a PL structure on P in a canonical way. So there is a maximal collection of polyhedral charts in which this map is contained. For this P, there is a maximum collection of polyhedral charts in which this map is contained, and that will give you a PL structure on this space. So that is what we mean by a canonical PL structure for a Euclidean polyhedron. And similarly, if you have any topological space and a homeomorphism to a Euclidean polyhedra, then you can use this homeomorphism to give a PL structure on X. You can transport the PL structure from P to X. In the obvious way, you have these embeddings of this, but this is a homeomorphism, so you compose them. So this gives you a PL structure on X, which is borrowed from a Euclidean polyhedron. So such spaces you will call polyhedron. Right. And you will call it a D polyhedron if the maximum dimension of all of these charts is D. Okay. So now we talk about an equivalent way to think of PL structures. So you see, this is very abstract. Maximal collection of polyhedral charts, and it is not very nice to work with because too many things. So what we want to do is sort of approximate polyhedra or spaces with PL structure using simplicial triangulations. And the way to think about it is, if your space is a PL structure, that means it has a triangulation, simplicial triangulation. But if you can obtain if you have two triangulations and you keep subdividing so that you get a final triangulation and you get the same thing for both of them, then you don't want to distinguish them. So essentially, up to subdivisions, you don't want to distinguish between triangulations. That is another way to think about PL structures. Well, it's not immediately clear from this how that is equivalent to this, but that is how we will use PL structures mostly. So we'll, yeah.
By dimension, you mean that Arden, that ambient space?
No. The dimension of a polyhedra, so polyhedra is defined as, oh right, so, okay. So, you mean the dimension of Euclidean polyhedron, right?
Yeah.
So, Euclidean polyhedra is the union of these cells. Now these cells are convex also of these finitely many points. So let's say you take En plus 1, subtract it with all of these, and that's a set of vectors. Its linear span, the subspace generated by it will have some dimension. That is the dimension of a polyhedra.
Okay.
Of a Euclidean cell. And for a polyhedra, it is the maximum dimension of all of these.
Okay. And for a polyhedra, okay, you have the maximum among these.
Yeah, among these.
So there are only finitely many of these.
Here, no. This is a maximal collection. This can be huge. It has in fact everything that you can imagine. If you, a sphere, for instance, you can have very fine ways of triangulating it. So everything is there. It is a huge set. So that's why I said it's very difficult to work with this definition.
Somehow the dimension is predefined.
Yeah. So that's true. So I mean, when I say dimension of a polyhedron, I mean that, well, all of these the dimension is not equal to that. Yeah, of course it may not be. I mean, the point is, if you have a point and then a line in a two-dimensional thing, this entire thing you can say it's a PL structure, but you won't be able to embed it in any RM. So that is not the kind of thing we are working with. So right now, so a D-dimensional polyhedron is, well, anyway, for specific PL structure, the dimension may not always be defined because of what you said, but for polyhedra it is defined because P is anyway in some RM. Okay. Right. So now here's the thing. So first proposition. So now K, L are polyhedra. So instead of X, I will write K, L, etc. So these are polyhedra. So now this is PL. If and only if there exists simplicial V and W and G from V to W simplicial such that So that means that so as I said, a map between polyhedra is PL. If you have some way of giving a triangulation to this and triangulation to this, under which it actually looks simplicial. So in this sense, instead of working with PL maps between such abstract objects, you might as well, if you want to check something, I mean, it doesn't mean, it is not any easier to check because you check for all, I mean, in the worst case you have to go through everything, but that's not possible always. So this is, but anyway, this is somewhat more concrete than that. Okay. And this is how we will most often use this. Okay, so as I have remarked earlier, now we talk about PL manifolds. Now PL manifold, so for this I'll write P, okay, no, M, etc. So PL manifold M of dimension n is an n polyhedron K such that the link of every point is PL homeomorphic to either Sn minus 1 or Vn minus 1. B is just a disk, S is just a sphere. Now what do you mean by link? As I said, you can think of polyhedra as a space with a triangulation such that you don't want to distinguish triangulations under subdivisions. So you have some triangulation. With respect to that triangulation, you can talk about link. Link is just you look at that point, you take a triangulation such that that point is a vertex. You can always do that by subdividing. Now, once that is a vertex, you look at those cells in which that point lies as a vertex, and for each of those, you look at faces which do not contain that vertex. That is a link. So, as an example, if you had something like this for the plane, this kind of a triangulation, and for this point, this would be the link. Okay. Oh, okay. Anyway, so now one thing you might wonder is, well, this depends on the triangulation, and if I want to define for polyhedron, it should not depend on the triangulation. Well, the truth is it doesn't. So I mean that's also a result. But yeah. So this is up to PL homomorphism. It doesn't depend on that. Of course. So also these points I'll call boundary points, points for which this happens, and these are not the boundary points, regular manifold-like points. So, for example, in a two manifold, if a point is somewhere here, then if you subdivide enough, then you're going to look like this, which is S1, and this will be an interval, which is B1. Okay. Some example. I mean, I already used this, but Bn is just this, and Sn is just boundary. Right. Okay. So now, smooth manifolds are also PL manifolds. So there is a canonical way to put a piecewise linear structure on a smooth manifold. I mean, it seems reasonable because locally they look like Rn in a smooth way. So I mean, this is not something obvious, but this is true. Every PL manifold is, of course, triangulizable. And these are, of course, topological manifolds. So this is always true. Every smooth manifold is a PL manifold. Every PL manifold is triangulizable because I have a because ultimately these are manifolds with simplicial triangulations under some subdivision, under some equivalence of triangulations, and of course these are topological manifolds. Now, in dimension 3 and less, so in dimension 3 and less, these are all the same. So every topological manifold is a smooth manifold and yeah.
When you said that we are defining, we look at them as simplicial complexes. The PL maps look at them as simplicial maps.
Yeah.
So you already have a triangulation inbuilt when you are looking at the PL map.
I have a PL structure.
Yeah.
It may not be immediately clear why from a PL structure we get triangulation, but this is true.
Yeah. So then over there, so you are saying that so when you are proving that smooth, so the proof of smooth manifold implies PL manifold.
Yeah.
Is that without using the fact that smooth manifold are triangulation?
Probably not. I'm not sure. But yeah. I mean, I think the proof of these two things are essentially the same. Because once you have simplicial triangulation, then you have right. I mean, I'm just writing it like this. There is no actual difference between these two. This is just when you see. Here you're thinking of them as with a PL structure. Here you just say there is a triangulation. There is no actual difference anyway. Right. So we'll make use of this eventually. Now, so now we know what polyhedra are, and now there is an operation in polyhedra, which is so K in a polyhedra. You say K, there is an elementary collapse from K to L, or an elementary expansion from L to K, if K is so you have Bn minus 1 sitting inside Bn and L, and you form the corresponding attaching space. So if this is true, then you say that you can expand L to get K or collapse K to get L. But this is an elementary collapse. This is like one step. Now, all of these maps that you have, we are assuming they are PL. So that when you form this is also polyhedron. Okay. Now, one thing you immediately notice is if it is possible that you have K, if there is an elementary collapse from K to L, then there is a point in K whose link is which essentially looks like a point on a PL manifold, a boundary point on a PL manifold. So you have a point whose link is Bn minus 1. What is that point? Just take a point here. Take a point here outside this. That is essentially looks like a point on the on the boundary of this outside design. Right. So of course, if you want to test whether you can collapse something, and if you look at the link of every possible point, if it is not this, then you know you cannot collapse. Okay. Again, some observations. So now this, without the P, means that there is a sequence such that each successive one I have this kind of collapse, and in the end I get this. So this stands for A equal to A0, from which there is an elementary collapse to A2, from which there is an elementary collapse to A3, and so on. In the end you get B. Finite linear steps. This implies this is here because this is just of course, first of all, this is a polyhedron, and then you do the same operations here. Just increase the dimension of all the cells by 1. So this is F. A is called collapsible. If you can collapse it to a point. and we say A and B are simply homotopy equivalent, they are polyhedra. If you have a sequence such that at each step either you are expanding or collapsing. So you should notice that whenever this happens, the homotopy type of the space does not change, because you can always retract this onto this. And in fact, that's why you're calling it simply homotopy equivalent. This is stronger than homotopy equivalent. Yeah. So similarly, there is a notion of simplicial collapsibility. So this is for polyhedra. There is a notion of simplicial collapsibility where you have a fixed simplicial triangulation, and you have a very similar thing, but instead of BA minus 1, what you have is this, which is the tetrahedron minus a face. Boundary of a tetrahedron, boundary of a simplex minus a face. One example is this. So you glue all these three sides and you don't glue this one. So here you choose a face and do that, don't do everything else. There you glue all of these three things, don't do this. It's the same thing, but you have a fixed simplicial triangulation in mind when you're doing that. Now you might ask whether, so and you have all these analytic definitions. Because once you define this, and everything else just makes use of that. So now a natural question would be, well, if something is collapsible, is it simplicially collapsible? So take the polyhedron, which is collapsible by that definition. Then you can find enough subdivision so that it is in fact simplicially collapsible. Right. Sorry. Yeah, that's fine. Now, this sufficiently fine simplicial triangulation is needed. If you have any random triangulation, it may not be collapsible. If you have a bad triangulation, so you have to subdivide it enough, then only you can ensure that it is in fact simplicially collapsible. An example, if you want to look into it, is so 3 days. Of course, it is collapsible. If you choose any triangulation, reasonable triangulation, it will seem collapsible. But Jordan gives the triangulation of this, in which it is not collapsible. Of course, if you subdivide it enough, it will become simplicity collapsible. Right. Okay, next theorem. Again, by White, right? Mazur and PL. PL are simply connected homotopy equivalent. So here we notice that if they are, if this happens, then A is homotopy equivalent to B. In this case, if they are simply connected, in fact, it implies that they are simply homotopy equivalent. If simply connected is needed, if they are not simply connected, there is something called Whitehead group, which measures the failure of this thing, simple homotopy equivalence. I myself don't know much about that, but we will need the result only in the case of simply connected polyhedron. And in fact, something more is true. If you let L be the maximum dimension of P and dimension of L, and if it is bigger than 2, then you can, in fact, you don't need to go more than L plus 1. So here, the maximum dimension of all of these AIs, you can take that to be L plus 1. So the point of view is, well, if you can go from here to here, that is something is collapsible even. Then that means there is some way of collapsing faces one by one, so that you get a point. If you make a bad choice at some point, you may have to go back, but that's not allowed. So you need to create room, basically, if you want to reach that this other thing. And what it says is you don't need to go in dimension more than one more than what you started with. But if it is actually 2, then 3 is not enough. You have to go in 4. Right. Is the result? And in fact, the conjecture is about 2 polyhedra. So something interesting happens in dimension 2. And finally, also one more thing I will just remind you of that. If you have 2 serial complexes and they are simply connected, and if you have a map from one to the other which induces isomorphism on all homology groups, then it is in fact a homotopy equivalence. So they are simply connected and you want to test whether or not they are homotopy equivalent. So if you can come up with a map which induces isomorphism on homology groups, then you know that the hypothesis is satisfied. So you can actually make use of that. So you know that in dimension 2 you sometimes need to go in dimension 4. Three is enough if and only if right. So what do I mean by this? So just like I had a notion of collapsibility for polyhedra and simple complexes, there is a notion for serial complexes which I will define in some time. But nevertheless, what this theorem is saying is you can do it just using in this way, which is more rigid, if you can do it for simple complexes. So this just means that you look at the simple complex, serial complex correspond to that side. This theory formula just means that this corresponding thing is simple homotopy equivalence, where the dimension is at most 3. Okay. Right. So far, all we have been doing is just lots of results and no proofs, but hopefully this gave you some idea of what this is about. Now we talk about regular neighborhoods. In PL manifolds. So what is meant by regular neighborhood? Suppose I have a polyhedron K inside a PL manifold. So the idea is I want to approximate this polyhedron using a submanifold. one way to think about it. So n, this is, of course I'm not writing it, but K is reserved for polyhedron and KL etc. and Mn are for PL manifolds. So M inside M is called a regular neighborhood of K. So this is a closed neighborhood. So what that means is this is a closed set which contains an open set containing n. If n in fact collapses to K. So you have n, a submanifold of m, and if you can collapse it to K, then you say that n is a regular neighborhood for K. K is a polyhedron, m is a K manifold. Right. In fact, something more is true. If you have n1 and n2 to satisfy this, then they are essentially unique. In what way? So then there is a PL homeomorphism which fixes K and which sends one to the other. So this is pretty strong, and we will make use of this a lot. But what this is saying essentially is, if you have a polyhedron sitting inside a manifold, then you can have, so this existence is there, you always have a submanifold and which collapses onto K, and furthermore it is unique in the sense that if you have any two of these things, then you have a PL homeomorphism from M to M which takes one to the other, fixing K.
There should be phi n1 equals n2, or should it be phi n1 equals n2?
Phi n equals phi n2.
Okay.
No, fine. You just make do it.
Oh right, sorry.
It's not the key.
Sorry.
Yeah.
Yeah. Science n1 to n2, right, sorry. Okay. K is called a spine if M itself collapses onto K. Right? It's very reasonable. And one thing you should note is, if M is path connected and boundary of M is non-empty, then there is a spine. So spine of M. K is called a spine of M if M collapses onto K. So if M is path connected and boundary of M is non-empty, then there is a spine of dimension less than or equal to dimension of M minus 1. So boundary of M, as I defined my different PL manifold, there were some points for which the link was PL homeomorphic to Bn minus 1. So those are boundary points. If it is non-empty, then there is a spine of dimension less than or equal to dimension of minus 1. Why is that? You take a boundary point and you fix a triangulation, you take a boundary point and you start collapsing one by one. You can do it in finitely many of these spaces. So eventually all the m dimensional ones will run out and you will have a spine dimension. So this is not a proof, this is only a sketch of a proof, but the essential idea is you need this boundary to non-empty to get started. Once you get started, you will never suddenly collapse something and the boundary will become non-empty or empty. Because whenever you collapse, this Bn minus 1 is always there. That will become the new boundary then. So you will always have points to collapse, and there are only finite many of these things, so eventually all the m dimensional ones will run up, will be over, and we will be left with something of dimension 1. Right. So this is, consider this. This is a space where this edge is identified with this edge and it is also identified with this edge. So you should say this is not a PL manifold. So because these points, there are three things attached to it essentially. So link of this point is looks something like this. So this is not a PL manifold because a PL manifold the link would have to be either a sphere or a disk. This is neither. This is not a PL manifold, and it is not collapsible because no matter what triangulation you take, these integral points, the link will be a circle. For these, the link is this, and for these points, you can again just convince yourself, and the link will be something like this. Because these two, if you go there, you come back from here, and this gives you back and forth. So this is the link. Let's call this Q. So link is either a circle or this or this. So you cannot collapse. It is not collapsible. Although it is clearly contractible. Because what is the identification map? A and A inverse. So it is homotopy equivalent to A, and the corresponding spaces have to be, attaching spaces have to be homotopy equivalent. So, and for that you just get this. So this is contractible, but not collapsible. So this is the simplest example that you could come up with of a polyhedron. This is in fact a polyhedron, which is not clear, but you have to take my word for that. Which is in fact contractible but not collapsible. Okay. So this the thing is this was not a PL manifold. Now the question is which PL manifolds are in fact collapsible. So now K is inside M and K is in fact collapsible. Then N, which is a regular neighborhood of K, is PL homomorphic to a disk. So this is the first thing that will actually prove, and you realize it's kind of cheating when I prove it, but let's see. So N is the regular neighborhood of K. So N collapses to K, but K is collapsible. So it collapses to a point. But regular neighborhoods are unique. So for a point, you know that if you have a really small subdivision, then because you are inside a PL manifold, which is M, then its length will be a sphere and its star will be a disk. This is a polyhedron, collapses onto it. So N will actually have to be PL homomorphic to a disk. So I mean it is not it is what it is. We are making use of the fact that the regular neighborhoods are unique. Okay. So now as a corollary of this, we immediately get that is collapsible if and only here on a vector disk, because then it is its own, it is the regular neighborhood of a point. Right. So I mean you must have realized it, what this proof is strongly using the uniqueness of regular neighborhoods, which we did not prove. But okay. Now here's something we'll actually prove. So suppose that the elementary collapse from L to K, and L actually collapses to a point. That implies K cross I collapses to a point. So what this is saying is, if you know that L collapses to a point and you do an elementary collapse, well, if you are lucky, then you can keep collapsing that K to a point. But even if you made a bad choice, you can still recreate room by taking the product of the interval, and that will collapse to a point. So the proof is not hard. So what do? This means that K is so now Bn is sitting inside right. So Bn is sitting inside K, and its inclusion is PL that we assume. So you get a triangulation of this which respects this. But then, so let's say T is that triangulation. And for every sigma in T, such that sigma is not contained in Bn minus 1, collapse and that is the proof, because whatever is left is just this Bn minus 1 plus the interval, which is nothing but Bn. So up to PL homomorphism, it is the same thing. Okay. So what this is saying is, if I know that the polyhedron is contractible, then so what was this saying? It was saying that if L was collapsible and I made a bad collapse, elementary collapse, then I can recreate room by taking product of the interval. What this is saying is, if I know that my polyhedron is contractible in the sense of homotopic, then if I take the product of the interval enough number of times, then I actually become collapsible. So it's about how much room that you need to create to actually become collapsible, given that you are contractible. So proof is easy, but assuming something that we did not show, what is it? Well, let's say K is a polyhedron, so K is now simply overfitted into a point. By the theorem of Poincare, because simply connected and it's simply connected and it is contractible. That means it is in fact simply homotopic into a point by the theorem of Poincare. And once this is the case, then if you remember the definition, that means we can start with K and we have a sequence like this. And in the end I have a point. Well, as long as I am collapsing, it's fine. The moment there is an expansion, I just look at this. Yeah, there is an expansion. That means that the product of this with that will actually collapse back to this point. I hope that is clear. What I am saying is, I start with K0. For every collapse, I do nothing. For every expansion, I take product with the interval and then appeal to this result. So now with all this, we can finally see what the conjecture is.
First proposition was if we already knew that L was collapsing to the point. But here we're using that, I mean, and then L to K should be a single collapse.
You can start from right to left in that case. I mean, yeah. Start from right to left and
Like
right. Yeah. Yeah. So yeah, this is the conjecture. Now, okay. I'm sorry about that. So yeah. So one thing, if the dimension is bigger than or equal to 3, then it turns out that you can take R to be 2n. You don't need to go beyond 2n. If R is equal to 2, it can be shown that 6 is enough. You don't need to go beyond 6. So there is something weird happening in dimension 2 always. But yeah. And this conjecture for n bigger than 2, this is not true. So you can come up with counter examples of contractible polyhedra such that this is not collapsible. But for 2, we don't know yet. And also this conjecture is so strong, as you will see shortly, that people believe it is most probably not true. But we don't know that yet. So yeah. So I want to give an example of this. So we look at the Dunce Hat. So what have I done? Dunce Hat was this case. I want to glue this and this. So I create a tetrahedron. But then I also have to glue this bottom edge. So for that I subdivide this into 3 parts. This is the same as Dunce Hat. I want to show this cross I is collapsible, which means I want to show this. So I will in fact show this, which means that there is an L which I can expand K to so that it becomes collapsible. What is that L? That L is the following. Remember, this is a 2-dimensional thing. I don't have the inside, only the top faces, not even the bottom face. I do this expansion, I attach a tetrahedron here. This is my L. Now I look at this face and I collapse using that face. By this face I mean the face to the right and behind. If I collapse using that face, that goes away. So what I'm left with is 2 faces like this. Then I collapse using these 2 things. So what I end up with is I do 2 collapse. So I end up with this thing. So the idea is I did not have this initially, this face. So I add a tetrahedron and then I use the other faces to collapse. And now this C is already identified, so we forget about this. So what this ended up doing is it freed this edge C. C was not initially free, but after this collapse, C is now free. So I can actually collapse using C. So now what I end up with is this C goes away, and this whole face also goes away. So what you end up with this, and then now it's pretty clear because you can now collapse using this, keep repeating because this is free now. So eventually, it all becomes something like this, which is collapsible. Okay.
I have a question. So, this theorem doesn't need that it is a two polyhedron, right?
Yeah.
And so we can ask the same question for any dimension of polyhedron. So, are there easy counterexamples?
Not easy, there are counterexamples. I said this. For dimensions bigger than 2, this is false. There are counterexamples. I mean, you can look up the counterexamples in the references that are given here. Yeah, so this is considered for dimension 2. Okay, so that was more or less what I wanted to say about this conjecture. Now I will talk about how this is related to group presentations. So what is a presentation for me? A presentation of a group is a bunch of symbols and a bunch of other symbols. These are we call as generators and these are we call as relators. But except these are not words here. These are just symbols, and I want to treat this. So what the information is, for each of these symbols I have a word in exile. So Ri is associated to a rho I, and this rho I is actually a word in the exile. So why do I want to make this distinction will be clear soon, but just to give you some examples. This is a presentation. Just X, one generator, one relator. Now I could write X inverse here. This is again a trivial group, but I want to treat this as a different presentation. Again, this is the same trivial group, but this is a different presentation. We are treating it differently, that's the point. So, adding letters which are already there is not allowed. So, one relator, one generator, but that generator, one generator, one relator, that relator is actually the empty word. Now, this might seem like a funny way of writing the empty word, but again, these two we are treating as different presentations, even though they correspond to the same group. And finally, something we are not treating as different is the following. So this word where you insert the empty word in the middle, this is the same as this. We are not trying to distinguish these two, but these we are distinguishing. And corresponding to each of these presentations is a way to create a serial complex. What is it? I start with a vertex. For every generator, I attach a loop. And for every relator, so how does it work? So I have a point which is 0 cell, and for each of the generators, I have these, and so on. All of these get mapped to the vertex, the single vertex, the boundary points, and for each of the RIs, I have 2 cells. And so on, and the words which are associated to RIs are written at the boundary. So if my word was x by x inverse, I'll write it in the boundary. And what this word is saying is, it is giving me the attaching map. So it tells me how to attach this boundary to my serial group complex. And in the end you get a space, that is a serial group complex associated to it. Now if there is nothing, so if the word is the empty word, then I send it to the vertex. So now what does that tell me? For each of these, let's see what the spaces are. For this one, the space is pretty clear, so you have this. And this is for both Q and P. They both correspond to the same space, even though the words, the presentations are different. Now, this corresponds to a sphere. Why? Because I attach this twice. So this becomes a sphere. Even though the associated group is the same, they are not the same space, not even at the homotopy. Now we go a step further. Now this is I have a vertex. For this generator, I have this loop, and for this generator, I have nothing. So what does that mean? I had a 2 cell. I have to do something with it. So I attach the whole sphere with the boundary to this point. So now what is this? This is S1 wedge S2. So again, the fundamental group is again Z, which is the same for all of these things, but the spaces are going to be different. For example, for these two, now the space is a pinch sphere. Why is it? Because if you think about it, this is the 2 cell that I am going to attach, but now I will attach and then do the inverse. So this whole part will get attached to the loop and then I start coming back. So that means this gets attached to this gets attached to this gets attached to this, and so on. So what does that mean? I get a sphere, except this and that are the same point. So what do I get? I get a pinch sphere. So to draw it, it looks something like this, where this is everything is attached. So now I want you to focus on these two examples. So these are different presentations, but I got from here to there by cancelling. Notice that these two squares are homotopy equivalent. Why is it? Because I can imagine moving this so that it looks like this. This is something that's done in any basic algebraic topology course. Then I can send this inside and then collapse, which will give me a pinch sphere. So this is what we are going to generalize in the next 15 minutes or so maybe. So I will just say this, I won't write it down. So now there is a way of going back also. So of course you should notice that not all three of the complexes will be obtained in this way. Anything beyond dimension 3 will not occur. So, but we are going to allow dimension 3 in the complexes that we look at. So here are some properties of the complexes that we look at. It will have only a single vertex. It will be 3-dimensional. And the way attaching maps work is the boundary points of all of the 1 cells will map to the same single vertex that is there. For every 2 cells, I will subdivide its boundary into small segments, and that segments will map to either 1 cell or the vertex. And I have 3 cells whose boundary will be a 2 complex. Those 2 complexes, the faces will map to these RIs, and vertices will map to this vertex, and edges will map to either this or that. Same assumption. So these are the complexes that we look at, and this collection we will call C. And for every 2-dimensional complex inside C, you have a corresponding presentation as well. So you can go back and forth. And now the question is, and again, so now inside this C, you can define collapsibility and deformability. Sorry, collapsibility and collapse and expansion. What is that? It's the same definition, except that now there the attaching maps have to respect this way of attaching. So that what you end up with is inside this C. So again, you see, we are not allowed to attach a 4 cell because that will go beyond dimension 3. So remaining inside sleep, we do all these operations. So we can do 2 expansion, 2 collapse, 3 expansion, 3 collapse, but not 4 expansion, 4 collapse. 1 expansions do not exist because that will mean yeah, that is one thing about it. I mean, we are assuming there is a single vertex, so this cannot go anywhere else. Right. Okay, fine. So now the main question is expansions and collapses. What does that correspond to for presentations, for group presentations? As you see, not everything is allowed. This cannot be allowed because that gives you a different space of homotopy type. So of course you won't obtain that by expansions and collapses.
Is there a correspondence between group morphisms and maps between certain functions in C? Is the construction control?
I mean, it is right because essentially it is a fundamental group of the space. The group is a fundamental group. The presentation is, I'm not sure. The presentation is just, we need to see, the point is, even the same spaces as of now do not correspond to the same presentation and vice versa. If by spaces the notion of equivalence is mode of equivalence, let's say. Right. What do you mean by that? These two, the words as presentations are different, but as spaces they are both the same thing. So this notion of functionality can come only after we know the right equivalences in both of these cases. That is the idea for now. We want to understand which spaces, expansion and collapse, what happens in the group presentation for expansion and collapse. And of course, if you want to only look at the group, then the construction is factorial, which is a fundamental group. But the presentation is quite subtle. In fact, that is the reason why I want to distinguish these things, because these are the same group. If we didn't distinguish between them, then there is a problem. Okay, so now I have to speed up a bit. So I won't be able to provide all the proofs. But first thing, some operations. You will have to cyclically permutate letters of each to y. Why is that? Because that is like rotating your cell complex before attaching. So it won't affect the space at all. What is the second thing? You can replace your y by its inverse. Why is that? That is like looking at, that is like flipping the complex before attaching. Again, doesn't affect the space at all. Now here is where some interesting things happen. So add an relator alpha and the relator w alpha w. Doesn't matter because cyclically permuting will anyway give me the same thing. But now 4 is the opposite of 3. Okay, so now what happens when I do this? The claim is it corresponds to this 3 corresponds to a 2 expansion and 4 corresponds to a 2 collapse. Why is that? So I'll just give a rough idea of why that is. If this is your K, let's say, then and you have a word like this. So corresponding to a word, I have lots of these one cells, but for simplicity, let's just think of it as this as being the word. And if you do a 2 expansion, that means you have something like this. So that means I can think of this as my alpha and this as my word W. So adding it as a relator means that this whole thing is attached to one thing, and this is my alpha. I hope this makes sense. The other way also is true. If you have two expansion, it has to look something like this. The free face, we will call it as alpha, and the faces which are attached will correspond to some words, because ultimately this attaching is inside C. So the way this attaching works is by the operations that I described. So that will give you a corresponding word. So two expansions are taken care of. So if I can start with a space and 2 deform it to some other space, by 2 deform I mean expansions of collapse, the same as simple order of equivalence, then all of that can be done using these 4 operations on presentations. Now the actual question is, what happens for 3 expansions and 3 collapses? And for that, we need a new operation, which I call the 5th operation. So what is it? It's somewhat involved. So rho is allowable. So start with the empty word and keep inserting x inverse x or x inverse as many times as you like in wherever you want. Choose Ri and form and call this word x, S. Whatever you end up with is S, and look at S rho I prime, S prime y prime. What is S prime? S prime is any cyclic permitted any word that you obtain by cyclically permitting the letters, and rho I prime is any word that you obtain by cyclically permitting the letters of rho I. Consider this. And then optionally perform any cancellations. So you insert it as x inverse lots of times, and you permute it and multiply it. Now you can cancel if you want, any number of times. And then repeat. So do this one and 2 as many number of times as you want. And then you get something, and the operation is, you say rho is allowable. Okay, flow is allowable if it is obtained by using these things, and the operation says that if in the construction of rho you use Ri only once, so you might have used some other Rj's other number of times, many number of times, but if you use Ri only once, then you can replace rho I by rho or rho inverse. It doesn't matter because inverses are always there. Okay, this is the operation. Now quickly I want you to show how this corresponds to 3 expansions, 3 collapses. Okay, so before that I should tell you something. So there's a lemma that says if you can start with a space and do a 3 deformation, end up with some other space, then you would have done some number of expansions. If you can do this, then you can in fact do this transiently. What that means is every expansion is followed by the collapse of the corresponding cell. So if you expand something, the next step is to collapse that same cell, possibly using some other phase. what the lemma says is, if you can do 3 deformation, then you can do a transient 3 deformation. A deformation in which each expansion is followed by a collapse of the same cell. Now, I'm not going to do the proof of that because we don't have time, but the proof is, the idea is very simple. You already have one way of deforming, now you want to construct a transient deformation. So, every time you attach a 3 cell, you attach a corresponding 3 cell here, but collapse it immediately. So, eventually in the original deformation also it is collapsed. So, it is collapsed by some phase. You use the same phase to collapse it. Now, the only issue is, let's say you have D1, when you attach D2, the phases that D2 gets attached to might be collapsed here already. So, for that, you just notice that, well, every phase by which you collapse is inside some cell. But because you collapse F by because you collapse E by using F, then this maps to this. So that can tell you where this phase which is collapsed is going to. So instead of sending your boundary, if something is attached to F, instead of attaching to F, attach it to this. And then keep doing this. You can show this works out, something need to be checked, but anyway. And so we'll show that this corresponds for transient T deformation. Okay. So, how does it work? So I have this S. So I'll give an example to illustrate how this works. So suppose my S is something like this. Suppose this is my row, and in the first step I multiply them by secondary primitive, so I don't compute anything, I just multiply. And let's say choose to cancel a few things, so that I end up with is something like x inverse, y x inverse. So I cancelled these things, z y inverse z inverse. These things I cancelled, and I cancelled this y inverse as well. So what I am going to do correspond to this is, I'll take a sphere, I'll draw a tree correspond to this. So how do I do that? X. So x, y inverse, another x inverse, z, y, oh, there's another x inverse. X inverse, and then one more x inverse, and then z, y inverse, z inverse. Because this is a trivial word, this will be a tree. You will always end up where you started. Okay. And then multiplying by this and performing cancellations, you can think of that as something happening here. So what is that? So you see, z, y inverse, z inverse. This is the part that got cancelled. If you are cyclically permitted, you can just rotate this thing. So that's not an issue. Z, y inverse, z inverse. So what you do is, these four things, you use these same letters for this row also. So what else is there? Y x inverse. So you call this y x inverse. So I hope it is somewhat complicated, but all we are doing is the things that get cancelled. we are using the same tree edges for those things that get cancelled, so that you can erase it inside, which corresponds to cancelling, and what you end up with is a polygon on the boundary of which this resulting word is written. Okay, I cancel this y minus also. And then it's very simple. So for every step like this, what you do is you attach this. So you think of this as the boundary of a 3 cell. Now this is the face, you attach it. So it depends. You can attach it from outside or inside, doesn't matter. You attach it. How do you attach it? These tell you where to send it to, and you use a relator in the process. That relator tells you where to send this inside to. So you know where to send this entire thing, and you can keep doing this every time you repeat this. You do this for each of those steps, and in the end, if you use something only once, then that corresponding phase will be free. In terms of 3 deformations, you can do a 3 deformations in that. If you use it only once, then from both sides will be something, so you cannot do it. But if you use only once, then it will be free. And then you can collapse. That whole operation corresponds to doing this. The other way is also true. If you attach a 3 cell, then you will be attaching the boundary of sphere minus a disk. That sphere minus a disk is a PL manifold with a non-empty boundary. So I can start collapsing and construct a spine. That will be a tree. So I can write down a word corresponding to a tree, and then every time, so I attach these cells and I expand the tree one by one. The same thing I did here. So yeah, that will correspond to this. So now this is kind of all that I wanted to do about 2 presentations, except for one last thing. So after this, so it's fine. So now these are the 5 operations that I have that correspond to 3 deformations. And if you remember, there is a theorem that I stated. You can deform 2 polyhedra. You can do 2 polyhedra are simply homotopy equivalent with maximum dimension 3 in all these things. If you know, you can do it for 0 complexes. So now what are some consequences of these? So you can do cancellation, for example. Why is it? If I have something like this, then I can do 1. Cyclically, I can send this to this place and I can call this W. And then by doing a 2 expansion, and now 5. If I multiply it by multiplying these 2, this will get cancelled and I'll end up with X inverse W. Which is the same as, which is W is just UV. So you can cancel these things. VU, but cyclically imperfect. So you get this. So cancellations are allowed. So this tells you that in the beginning, when we are looking at examples of presentations, we cancelled X inverse X to get 1. That this tells you that those 2 spaces had to be homotopy equivalent. There's no other option. Okay. Similarly, you can do conjugation. Why is that? Because rho you can send to X inverse rho because of cancellation, but then you can permit cyclically. This is also fine. And then you can form products also using 5. I will not go into that. So what do I mean by that? You can send rho I, rho j to rho I, rho j and rho j using 5. Because you will start with the empty word, then use this rho I generator, do this whole thing, and in the next step you will use your rho j generator and then stop there. Okay. So now the thing is, these operations. in opposite of 4. You have 6 operations that you can do. These are all allowed from our 5 operations. Turns out that for spaces which are simply connected, this is all you can do. Why is that? Because first of all, everything except 3 and 5, you can do using these operations. Now you can do 3 and 5 also, because this W that you use in 3, that W is actually products of conjugates of Ri, because your group is trivial. If your space is simply connected, the group is trivial, so R by itself is a product of conjugates of this, so you can do this, and something similar you can argue for 5 also, so I will not go into that. So for simply connected spaces, this is all you can do for deformations. And that shows you how this Zeeman conjecture implies Andrews-Curtis Conjecture stabilizations. What does it say? It says that if you have a presentation like this, so now I'm just writing Ri, these are okay. So now this n and that n are the same. If you have the same number of filters as the number of generators, then this space is in fact contractible if the group is trivial. Why is that? You can do a computation in cellular homology to see that. So all you have to do is you have to show that the second homology group is trivial, because all the others are anywhere 0 and this is simply connected. So by Whitehead's theorem, that will tell you that the inclusion of a point is homotopy equivalence. That will tell you that this is in fact contractible, the corresponding polyhedron. So you have to show the second homology is trivial, and for that you can do cellular homology. So I will not go into the details, but because these things are the same, this n and n are the same, you will see that the second homology is trivial. If you start examining the kernel, you can do some computation, because the Ri's will actually span this whole thing. Okay, I will not go much into that, but this is trivial, implies that the commutator, the abelianization of this is trivial, and the abelianization will have some number of some relators here. Now those will be the coefficients of the matrix corresponding to the kernel of D2, del 2 into some homology. So I mean, I will leave it to that. I will leave it to you to do that. And that so this shows that if your group is trivial, if such a group is trivial, then you can actually do these 1 to 5 one by one and end up with a trivial group. Why is that? Because if it is trivial, that means that by Zeeman conjecture this collapses to a point, its dimension is at most 3. So that means this is 3 deformable. So that means this is 3 deformable. That means these 5 operations are enough. Okay. So this is all I wanted to do for group presentations. Now we come on to something rather interesting. So I'll just take 5 to 10 more minutes and that should be enough. Okay. So let me start by writing some nonsense, but we'll try to see what's useful in that. So let's see. So 1 is the same as 1 minus 1 plus 1, but that is the same as minus 1 plus 1. So you keep doing this. So don't yell at me right now. Let's see. So now you can group these two. So you get 0 plus 0 plus 0, and you get 0 in the end. This is of course nonsense all I have written here. But what exactly is the issue with this? The issue is not that you cannot group these things together. The issue is this thing doesn't exist, it doesn't converge. So both sides are actually should be infinity. But the point is, you don't always have to worry about convergence. When you're doing algebra, you don't have to worry about things like convergence. So in cases, this trick is actually useful. An example of that, for example in commutative algebra, is the following. So let me show you. So if A is a projective module, that implies there is a free module such that that's isomorphic to F itself. So you know by projective there is a B such that A directs on B is actually some free module. So this implies there is a B such that A directs on B is free. This we know from definition of projective. I mean one of the several definitions of projective. But what does this imply? You look at this thing. A plus B and keep doing this. This is also free because there are some free modules. But then if you just group these things slightly differently, what do you get? So call this your F. This is equal to A plus F. Why? Because each of these is the same as A plus B. So if you think about it, the thing is this convergence, there is no notion of convergence or anything. You are not worrying about all these things. This thing exists, and because this exists and similar operations you can do, you can prove this. So this is one example. I'll give another example of this trick, and this is something in set theory. It's called Jordan-Curve Theorem. If you might know it, you might not know it, it's fine. It says that if you have injections from x to y and y to x, then there's a bijection from x to y. So let me write disjoint union as plus and equal to as existence of a bijection from one side to the other. So y injecting into x means x is equal to y plus a. And x injecting into y means y equals x plus b. Right. So now that means that x is equal to a plus b plus x. Because y is x plus b and these things I can disjoint union the same. Now I repeat this. So I keep repeating this. The formula to this would be an arbitrary union of lots of things. This infinite sum is nothing but a union. So this is no problem. There is no problem in well-definedness or anything. It's all fine. And there is something that is remaining in it. So union of all these things plus something that's left. That is my x. Now y is x plus b. So y is b plus x. But what is x? A plus b plus a plus b. And now you can again do the same thing. You can group these things like that, and you get a plus b, and so on, which is nothing but x. So I'm going to write down these things properly if you want to, but assuming this is the idea, and this is what you do in the standard proof also. It's just written differently. So this trick is very useful, and we are now going to use this trick into something in topology. It's called okay. So I hope you all know the notion of connected sum of oriented compact d-dimensional manifolds. If you have two oriented manifolds, what you can do is you can take a small disk from one point, remove it, do something for the other one, and glue them so that the orientation is compatible, and you can give an orientation to the connected sum. That's called the connected sum. Thing is, you can do an infinite connected sum also. So you can view this connected sum as an appropriate push out. Your disk, there is an inclusion to the first manifold, the other manifold, and you're working with oriented smooth manifolds, etc. You can create an infinite diagram where this first disk is inside M and N, and then there's another disk inside N, M1, M2, M3, and so on. So you can look at an infinite diagram, and the corresponding push out will, let's say colimit will give you an infinite connected sum. Point is, the intuition for that is, for example, if you have a sphere SD and you do an infinite, so what does it look like? If you have a manifold like this and another manifold, then you just remove a small disk, and attach these two things. So sphere connected sum sphere is another sphere. This is also a sphere. And if you do it infinite times also, this is a sphere. The reason is not that this is limit or something is constant. The reason is that ultimately the categorical construction, what it captures is the following. So when you do it once, you get something like this. The next time you do it, you can imagine it as shrinking the size of the sphere every time you do it. So again, I am not justifying why that definition captures this kind of construction, but you have to take a word for that. So if you keep doing it infinite times, ultimately it's still a sphere. Okay. So this is a sphere. But what does this tell you? It tells you that if you have any M and N which are oriented compact full manifolds, and if of dimension D, implies so this is called irreducibility of the sphere. And how do we show this? The same way. Look at and so on. This is because this is sphere. This whole thing is the sphere. But then now you group these things like this. So this is just M and some with these things. And so on. But this is sphere, everything is a sphere. So it's just M. So similarly we do for N also. This is not completely precise. As I said in the beginning, I will only give sketch of some proofs, and this is one of the instances. Okay, so now we will see how this implies a generalization of Jordan Curve Theorem, which is called Topological Schoenflies. So let's see. So what this means is, for a sphere, if you have a circle inside it, it bounds to disks. In general, this is a theorem, and the proof is as follows. So it makes use of something called Alexander duality. If you don't know it, it's fine. I will. So all that is useful for is the following. So this is what it says. I mean, you can replace this by q and n minus q, but this is from Alexander duality. Now, this is Z means that the zeroth homology is that there are two path components. When you subtract this, the two path components, and if you take their closure, because they are made of locally flat, their closures are manifolds with boundary. Now the closures, the boundary is nothing but Sn minus 1, because you remove Sn minus 1. So now you attach disks to both of these boundaries, so that the boundary goes away and you end up with a manifold. Okay, so let's call those manifolds X and Y. But then if you think about it, SD is nothing but X and Y. X and some Y. But then by that, both of these have to be SD. But what was X? X was closure of one component, you attach a disk onto it. If you remove a disk, you get a disk again. If you remove a disk from the sphere, you get a disk again. So that's why this holds. Okay. And now finally we can show that Zeeman's conjecture implies the Poincare conjecture. I mean, not show it, but assuming Zeeman's conjecture. So I mean, we are showing that thing. Oh yeah, whatever. Okay. So what is Poincare conjecture? It says that any topological three-dimensional manifold which is homotopy equivalent to the sphere is actually homomorphic to the sphere. So I take something like that. This is homotopy equivalent to the sphere, and so first of all, because in dimensions 3 and less, everything is triangularizable, smooth, etc. So I can triangulate it and remove a disk, and remove, let's say, 3 simplex. So let's call it n. What you get after removing the disk, so s minus, this is called d, is m. Now this m is actually contractible. Why is that? Because by Van Kampen this is simply connected. You can check that all of its homologies vanish by mere rotor. So you only need to check it for dimension 3, I think, and for that, because this is homotopy equivalent to the sphere, it will follow. I'm not doing that, but that is very standard, so you can write it down and see why that is. But in any case, that shows that M is contractible. But remember, this is a three-dimensional manifold with boundary. So we cannot directly say by Zeeman conjecture M cross I is contractible because of not true in high dimensions. But however, as I said, there is non-empty boundary. So there is spine, which is dimension 1 less or even less. So there is K M, so spine, K is the spine, and dimension of K. So this happens. But now K, for K it is 2. But then because M collapses to K, this holds. But if you remember, this is a PL manifold now. And we know that only PL manifolds which collapse to a point are disks. So M cross I is a 4 ball. But then now it's easy because M is inside the boundary of M cross I as M cross 0. But boundary of M cross I is ST because M cross I was a 4 ball. And boundary of M was S2. So by this, we get that M is actually V3. But then if you attach a V3 to a V3, you get a 3 sphere. The way M was so along the boundary. So that shows that right. So this shows that Zeeman conjecture implies Poincare conjecture. One thing you can note is that in the proof we only need the result for those polyhedra which have spines of three-dimensional manifolds. So in fact we are not using the full power of the Zeeman conjecture, just for those which are spines of three-dimensional manifolds. Now it turns out that it is actually equivalent, and the Andrews-Curtis Conjecture with stabilization that we proved, that is equivalent to the result for those polyhedra which are not spines of three-dimensional manifolds. This is for those which are, that was for those which are not. And yeah, so that is the end of my talk. Thank you very much.
Any questions?
References. So by Zeeman himself. This is the paper in which he first made the conjecture. And then again by Zeeman himself. So these are notes that he probably made for the seminar, and it has a lot of results that we use today. If you remember, I gave at some point I said an example of a polyhedron which is collapsible, not collapsible, not simplicity collapsible, but collapsible. Polyhedron is collapsible but not simplicity collapsible. You have to come up with enough subdivisions so that it actually becomes simplicity collapsible. So that is. Okay. And for the part on group presentations and how they are connected to three deformations, let's see this. Finally, so a lot of my major portion of my talk was based on the survey of results concerning Zeeman's conjecture. So that is. Yeah.
Any other questions? Let's thank speaker.
Thank you.